Welcome back, students. Today we are going to continue our discussion of the chemical bond. So last time we developed some of this notation looking towards an H2 plus molecule, and we're going to continue that a little bit today and then extend this beyond the H2 plus molecule into larger molecules. And our focus today will be on homonuclear diatomic molecules, and then next time we'll look into heteronuclear diatomic molecules and see what we can do there. So the learning goals for today are going to be to continue this conceptual combining of atomic orbitals into molecular orbitals. Once we consider atoms larger than hydrogen or molecules larger than diatomic hydrogen, we're going to have to consider other orbitals other than the 1s atomic orbital. And we're going to actually get to MO diagrams, so you may remember doing this in other classes. We're going to go through it very briefly. It's the exact same in filling out an MO diagram as it is filling in an atomic orbital diagram. And we're going to get a little bit more difference to these MOs. So we're going to see some sigma MOs like we saw last time and some pi MOs for these larger molecules. And we'll continue working with these ideas in the next class as well. So we're going to start by going to the board for a little bit of math. So last time we ended by determining these two energy values. We had Eg, that was our bonding orbital. Remember that G stands for Gerard, it's a German word, and we had U for Ungerard, and they're talking about symmetry, not necessarily bonding and anti-bonding. And we'll see that a little bit more today when we discuss pi orbitals as well. So we had these terms for their energy. We could only calculate the average energy because that's all we had. Our wave functions were not direct eigenfunctions of the total energy operator, so we could only calculate an average energy. And we came up with these terms where our H's, these capital H's and capital S's here, are complex integrals as shown down here. What we want to do now is actually attempt to solve some of these integrals, again, in only a very qualitative sense. So first, we're going to try to figure out what the HAA and HAB integrals are, and then we're going to put those together to try to figure out what we can do and what we can say about these energies. So let's go ahead and evaluate the HAA integral. The HAA integral is shown here. The formula for all of these H integrals is shown here. And if we're using AA, that means we're using both centered around the same nucleus. So what we're going to do is integrate over the phi A, and remember phi A is the 1s orbital for hydrogen A. And then we're going to operate on phi A with the total energy operator for just the electrons. And then we'll integrate it over the respective variables. Now, our total energy operator is shown here because the molecule we're considering is H2 plus. So H2 plus has a single electron, and then it has two nuclei, and the total energy for that, for the electron, is the kinetic energy of the electron, which is shown here, and then the potential energy for the electron with nucleus A, and the potential energy for the electron with nucleus B. So if we plug that in, we'll get the following. I'm going to break this apart into two integrals. So I'll get the integral of phi star A, and then we'll have negative h bar squared over 2m times the kinetic energy operator there, and then minus e squared over 4 pi epsilon naught RA, and then phi A. And then we have a second integral that's going to be minus, and I'll actually, for space, so actually I'll move this all down. Oops. So let me move this down so they can all be in the same row. I'll have minus the integral of phi star A times the minus is already included, e squared over 4 pi epsilon naught RB times phi A. Now, what do I have here? This first integral is the integral of the electron around nucleus A. The other function is the electron around nucleus A. And in the middle, we have the kinetic energy and the potential energy dealing with the electron and nucleus A. So this whole first integral is simply the integral of the average energy for an electron in the 1s orbital around a single hydrogen atom. And we know what that is. So this first integral boils down to the energy of the hydrogen atom in a 1s electron, so E1s. We have this second integral that is not so nice. So what we have here is, again, we have the interaction of just an electron in atom A, but we're talking about its interactions with atom B here in the molecule. So we can't really solve this integral analytically to get a nice answer like we can for the first one. And so what we do is we say that this HAA is equal to E1s minus J. And this J here is the sum, is this whole integral. We just say that this guy is J. And we can see that everything in this integral is positive. So our J is positive. So when we subtract a positive number, that's going to lower the energy. So then we'll go ahead and do the same thing for HAB. And this will give us the integral of phi B star, the total energy operator for the electron, and then on phi A. And remember, this total energy, or this B and A here, are not referring to different eigenfunctions of the same operator. They're talking about wave functions centered around atom B and atom A. So when we go through this, what we end up getting is the integral of phi B star, and then we'll have minus h bar squared over 2m times the kinetic energy operator. And in this case, okay, so minus e squared over 4 pi epsilon naught RA. And then operating on phi A. And I'll bring this down again to the bottom, so they're all in the same row. And then we have this other integral that's equal to phi B star e squared over 4 pi epsilon naught RB times phi A. Now, what can I do with this? Well, this first integral I can do something interesting with. So here I'm operating on the wave function from atom A with the total energy operator for atom A. So that, of course, returns me the total energy of the 1s orbital. However, unlike in the last case where that left me with phi star A, phi A, which integrates to 1, I don't have that. So what I end up getting when I do that is the energy of the 1s electron times the integral of phi B star phi A. And we define this as the overlap integral. So the second term is, this first term is the overlap integral times the energy of the 1s electron. And the same thing that we did last time is we really can't get a nice solution for this integral, so we slap a new label on it and we call it K. So we have that HAB is equal to SAB times E1s minus K. Now, we have these integrals that are J and K, and we can think about them in terms of what they mean. So J is called the Coulomb integral, and it is talking about how an electron, if we model it as a diffuse charge, around nucleus A interacts with a different nucleus B. And we can get ideas for what this integral should be using modern electrostatic computational programs and such. However, K is a weird thing. So K is called the exchange integral, and it doesn't have any physical interpretation. It's simply a consequence of using quantum mechanics in an attempt to solve this problem. So what can we say about these two things? So using programs like Gaussian, we can show that both the HAA and HAB integrals have negative values, and that HAB is greater than HAA, the magnitude of that. So the magnitude of HAB is greater than the magnitude of HAA, which means that K, the exchange integral, is greater than J, the Coulomb integral. Using these definitions, we can understand what happens to our energy. And we talked about this last time. We're again going through a little bit more detail about how to get this. So what we can say is that our EG, right, is HAA plus HAB divided by 1 plus SAB. This is our definition of Eg. And now we have these expressions for what HAA and HAB are, so we can plug these in and see what we get. So HAA is E1s minus J, and HAB is SAB E1s minus K. This is all over 1 plus SAB. So then what we can do is factor out this E1s term, and that's going to give us E1s times 1 plus SAB. And then we also have, I'll factor out these terms, we have a minus J plus K term over 1 plus SAB. Here we can cancel out the 1 plus SAB for one side, and we get that the EG is equal to E1s minus J plus K over 1 plus SAB. So in other words, our Eg energy is the same as the E1s energy, and then lowered, because J and K are positive numbers, lowered by a certain amount. And this is what we expect based on the way we've drawn MO diagrams before, and kind of what we already talked about last class. Now we can do the same thing for EU and find out that EU being HAA minus HAB over 1 minus SAB is going to be equal to E1s minus J, and then minus SAB E1s plus K divided by 1 minus SAB. We can do the same factoring and get E1s 1 minus SAB, and then plus K minus J over 1 minus SAB, and then end up with our EU being E1s plus K minus J over 1 minus SAB. And remember, our quantum mechanical calculation suggests that K is greater than J, and so that means that this number over here is positive, which will shift the energy up. And since the denominator here is going to be smaller than the denominator for the first part for EG, then that will be shifted up further than EG will be shifted down. Going back to the slides here, we can get an estimation for what these wave functions are. And we can see that our EU wave function is always greater than 0. And what that means is that this EU orbital, this antibonding orbital, is always higher in energy than the two separate atoms. So this does not contribute towards bonding. However, the EG orbital has a region where there is lower energy than 0, which means, or in this case, the negative 13.6, which is the energy of a hydrogen atom. So in this case, we can have stable bonding in this EG orbital. This shows us that our H2 plus molecule actually forms a stable molecule if the electron occupies the lowest energy orbital, which is the EG orbital, and we'll call that sigma G, and we'll see that in the next couple slides. Despite the simple assumptions made in this model, the predicted energies that we get, so this sort of stabilization here, as well as the bond length, is actually pretty close to the observed value, suggesting that these approximations aren't too catastrophically bad. We can see what this looks like if we go ahead and compare the electronic functions as well as the potential. So the electronic energy function always decreases as the two atoms get closer together, whereas the nuclear potential increases, right, as we try to put two nuclei in the same spot. When you add these two things together, you end up with a happy medium here, where we have the actual bond length being the compromise between the two. Now let's turn to evaluate the wave functions relative to their atomic counterparts. So what we're doing here is looking at 1s orbitals for individual atoms and then comparing those to molecules. So this is the bonding orbital, and the blue dashed line is the 1s orbital if it were not interacting with another atom. So here we have one 1s orbital around electron A, and we have another 1s orbital around electron B. They look different than they had before because we are not looking from R goes to 0 to infinity. We're looking here at an R of 0, and then we're going to infinity in both directions. So they had this sort of peak rather than an exponential decay, but you can see that there are two exponential decays meeting at the nucleus. In the top here, we have the wave function, and in the bottom, we have the square of the wave function, which will be the probability density. So what you can see is that for the bonding orbital, there is more electron density between the atoms than we would expect from two separate atoms. There's also less density away from the nuclei than you would expect. So this is showing us what's actually happening in a bond is that we have a buildup of electron between the bonding atoms. And that is very in line with what we expect from a bond being a shared pair of electrons. We can see we get electrons more often in between the atoms than further apart from the atoms. Now, what about this anti-bonding orbital, this EU orbital here? In this case, what we're doing is adding two wave functions that are out of phase with each other. And this creates an actual node in between the atoms. So we see that there is a depletion of electron between the bonds here, and we get a slight increase of electrons further away from the nuclei. Now, this does increase the area, so we get some increase in area from allowing the electron to travel between the two, but we have this charge depletion here in the middle. This figure compares them to each other. So this is plotting the red curves and the purple curves. And again, you can see a great depletion between the nuclei, and the purple is more likely to be further away from the atoms than the red. And here in this last figure, what we're comparing is actually the difference between the atomic orbitals. So in red here, this is the normal molecular orbital, the EG orbital. And then what's shown here in blue is the difference between the atomic orbital. And the fact that this is positive means that we get a buildup in charge compared to what we would expect. So there's more electron density between the nuclei as we expect, whereas here in the anti-bonding case, there's less density between the nuclei than we expect for two separate atoms. How can we extend this information from our simple H2+ molecule to other molecules? Essentially, what we need to do is consider more orbitals. Molecules that aren't hydrogen have access to 2s orbitals and even 2p orbitals. And we're going to limit our discussion to those kinds of orbitals here. Now, if we're mixing these orbitals, we're not just mixing together 1s orbitals, but 2s orbitals and 2p orbitals. You know, what can we do? So we'll see that there are a variety of types of orbitals that we can get. So these are the ones that we've looked at before, and we talked about the symmetry. So here we had a G and U symmetry, and this was based on, does the sign change if we invert the point? So going from this point, crossing the nuclear axis and going to this point, we see that the sign does not change, it's the same. And that means that this orbital has G symmetry, and we can look, it looks like a nice anti-bonding or a bonding orbital. This orbital has U symmetry. As we change across the axis, we change sign, and so we have an anti-bonding orbital. Now, this is not the only type of symmetry that we can talk about. So these bonds, we'll call them sigma bonds. And they're going to be sigma bonds because if we were to physically rotate the bond, so if we were to take this bond and turn it around in the plane of the bond axis there, the sign doesn't change. And that's true for both of these orbitals. However, there are other types of bonds, and you remember these from organic chemistry, pi bonds, and these pi bonds actually change sign. So if we were to rotate this bond in the plane of the bond, this blue part would become the red part down here, and we get a sign change. So we give this pi, we call these a pi bond. Now, what is the symmetry of these pi bonds? Well, if I start here and then cross the plane of the bond, I end up changing sign. So this is a pi symmetry, and it has U symmetry. Now note that this is the pi bonding orbital. We actually have density between the nuclei. So we have a pi bonding orbital, but that pi bonding orbital has U symmetry. And of course, the anti-bonding orbital has G symmetry. If I cross the axis here, I have no bond, or I have anti-bonding, but I have a G symmetry. I don't change sign. So to denote anti-bonding, we will use this asterisk here because the U and G is not enough to simply do this alone, and this just helps us understand what's going on. So here we have a 1 sigma G bond for a bonding sigma orbital, and here we have an anti-bonding sigma orbital. Here we have a bonding pi orbital and an anti-bonding pi orbital. I'll talk about what the ones mean in a little bit here. So what do we do when making a bond? How do p orbitals actually contribute to forming bonds? Now, you'll remember that part of the bond is this overlap integral SAB, and that overlap integral needs to exist. There needs to be net overlap. It needs to be a positive number in order for molecules to overlap. So this means that you have to have the same type of symmetry in order to get a bonding orbital. If you have different types of symmetry, there is no net overlap. So let's go ahead and look down here at this figure. We've talked about how s orbitals overlap, and that's pretty good. But how does an s orbital interact with a px or py orbital? You'll see that if we try to put these together, there is positive overlap here, but negative overlap here, and that's going to cancel out. So there's no net overlap between s orbitals and px or py orbitals that have this pi symmetry. So there's no overlap, and we have no combination of orbitals between s orbitals and px or py orbitals. However, the p orbitals can interact with themselves, and the s orbital can overlap with the pz orbital. The z here is chosen to be in the direction of the bond, whereas the x and y orbitals are perpendicular to the bond. That designation is somewhat arbitrary. Another thing that needs to happen is that the atomic orbitals need to have similar energies. And another way of saying this is that they have to be on the same quantum number. So the 1s orbital will not form any overlap with the 2s orbital or the 2p orbitals. Now, this might seem arbitrary, but as we saw when we did quantum mechanical calculations for lab 2, we looked at some of those molecular orbitals in lab and saw that the lowest energy molecular orbitals were basically 1s electrons around the given carbon atoms that we were talking about. And we did not tell the computer to do that. It just did that by itself. These orbitals are so much lower in energy that they don't really talk to each other. So the only kinds of orbitals that are going to overlap then are going to be, 2s and 2s, and then 2p and 2p. And of course, we will see some combination between the 2s and 2p orbitals, depending on how close they are to each other in energy. So the way that we go about this is by simply constructing molecular orbitals, and then we fill that molecular orbital according to Hund's rules. So what do I mean? Here we can look at the formation of a hydrogen molecule. So we have a 1s electron from hydrogen A, a 1s electron from hydrogen B. We can construct our MO diagram. We get the Eg energy, which comes from the sigma bond and the bonding orbital, and then we have the sigma U anti-bonding orbital. And we fill this in, and note that when we make this molecule in this way, our electrons are at lower energy than they would be in the separate atoms. And so this indicates that H2 is a stable molecule. However, if we were trying to do this with helium, and we had to put 4 electrons, because there's 2 electrons for helium, we'd have 2 electrons in this sigma G orbital, and then 2 electrons in this sigma U antibonding orbital. And the net result would be that there's more energy in a diatomic helium molecule than in 2 helium atoms. So helium does not form a stable diatomic molecule. After our sigma U here, we have more types of bonds that are being formed. So in general, if we're forming higher energy molecules, say something like carbon, or nitrogen or oxygen. What we end up getting is a more complicated scenario here. So our 1 sigma G and sigma U orbitals are discussed here. And then what we start doing is merging 2s and 2p orbitals. So when we merge the 2s orbitals, we get another sigma bond that gives, and it's bonding. So we have 2 sigma G. And then we have 2 sigma U star, the antibonding orbital. Then we end up with a 3 sigma G, where again we have bonding here between 2p orbitals. Then we have our pi orbitals, or their next highest in energy, and then we have our antibonding pi orbitals. Now, the reason for this, why does the sigma bond from p orbitals come before the pi bond from p orbitals, is because the sigma bonds have more direct overlap. So that is more favorable and lowers the energy. So the sigma bond here between 2p orbitals has more overlap, lower in energy, and then the pi bond has less overlap, so it's higher in energy. And then the pi antibonding orbital has less overlap in the kind of antibonding way, so that makes it the next highest in energy. And then even above that, we would have a 3 sigma G antibonding orbital. And we'll go through some of this in class. Now, how do we go about filling these things out? Well, it depends on the molecule here, and we'll talk about why it depends on the molecule in the next lecture. But essentially, what we need to do is construct the orbitals. So we'll go ahead and look at fluorine, and we'll save nitrogen for next time. So we typically will ignore the 1s level because they are so low in energy relative to everything else. And we'll stick with just the valence electrons. And this kind of makes sense for what we're thinking about when we talk about bonding. So here we mix together 2s orbitals. We end up with a bonding orbital, a bonding sigma orbital, and a bonding antibonding sigma orbital. And then when we mix together the 2p orbitals, we have the bonding sigma orbital coming from the pz orbitals. Then we have 2 bonding orbitals that are the pi orbitals, and they are energetically degenerate. They're just talking about orientation. And then we'll have the antibonding orbitals up here. And the way we fill this out is the exact same way that we fill out any other atomic orbital energy levels. So we shift the bonding orbitals down in energy, the antibonding orbitals up in energy, and then we just fill them in with electrons. So fluorine has 7 valence electrons, so diatomic fluorine should have 14 electrons. And we just fill them in from bottom to top using our same rules that we've used before. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we get the MO diagram for diatomic fluorine. We'll talk about this in class, and we'll see this in the next lecture. But nitrogen is going to be different in the fact that for nitrogen, the pi orbitals are actually lower in energy than the sigma orbital. And we'll think about that. I'll leave you off thinking about that, and we can talk about that in class if we have time, or save it for next class. And this has to do with the interaction between the s orbitals and the p orbitals. So it turns out that nitrogen has some, the s orbitals and p orbitals for nitrogen are closer in energy than they are for fluorine. So that gives them more overlap. And that actually forces this orbital to go up. You can see from these lines here, we're talking about sp mixing. And maybe you remember this from inorganic chemistry or previous classes. And we'll talk about this next time, and maybe in class if we have time as well. So I'll stop here, and we'll pick up with this next time, and then also discuss heteronuclear diatomic molecules. And from there, we'll move into polyatomic molecules and see where our model goes from there.